forces that we have dealt with so far. Done. There are actually going to be 3 conservative forces that we will deal with in this class. That's the only one we've dealt with so far. So we've got this weight, then there's the generalized gravitational force. Weight's just a very specific case of it. Generalized gravitational force. And then ideal elastic / spring, which we get into in chapter, for some reason I'm thinking chapter 14 is when we'll first officially deal with it. Although as part of chapter 6, we will throw a spring into one problem. The classic skiing down the hill running into a spring problem. Non-conservative forces, all the rest of them. All right, so if we follow the train of thought, and unfortunately I erased it before I made this point, but presumably it's in your notes. On the left-hand side, we have work is equal to force times displacement. We worked all the way through it until we got to here. And on the left-hand side, we had K final minus K initial for side A. So the work, no, the total work actually, total work, is equal to K final minus K initial, or just change in kinetic energy. There are 3 work energy relationships. This is the first one. Non-conservative work. Well, that basically, we had non-conservative work acting on the box there, so it took energy away from the box. So non-conservative work causes change in energy in a system. So it just causes a change in energy, total energy. Now the total energy stays constant in the universe, but when we generally don't look at the entire universe when we solve problems, we look at very narrow, like box on table. We look at the box. We don't look at the table. So if we look at just the box lost energy because it transferred some to outside the box. That's what non-conservative work does. So my total work, well, I have only 2 types of work. I have conservative and non-conservative. So that's just my conservative work plus my non-conservative work. That's equal to the change in kinetic energy. Non-conservative work is just equal to the change in energy, so this is conservative work plus the change in energy is equal to the change in kinetic. Well, energy, I'm not worried about things bursting into flames or anything like that. We have no nuclear explosions here. So my energy here is just potential plus kinetic. So this is my change in kinetic plus the change in potential. So my conservative work plus that equals change in kinetic. This is like that. My kinetic energies will cancel. I'm going to bring delta U over to the other side. And so I have my conservative work is equal to the negative change in potential energy. Those are the three work energy relationships. The first one, though, that the total work equals the change in kinetic energy. This has a special name. This is known as the work energy theorem. I think it's a horrible name, but it is what it's called. I think it's a horrible name because, to me, it's true because we define work and we define kinetic energy to make it work. I don't know why it's a theorem. It should be the work energy definition. And one other bit of vocab, because you can't get too much. Hewitt will sometimes make reference to mechanical energy. Mechanical energy is just kinetic plus potential energies. In other words, mechanical energy excludes rest energy. And we don't need to worry about rest energy unless something, again, bursts into flames. Or we're dealing with particle physics. And I think on that note, let me hand quiz 3 back. And at this point, all of you can still make an A and all of you can still fail. This quiz is just a drop in the bucket, which is good news for some of you and not as good news for others. So next time we'll start out with any questions concerning the test. So however long that takes, I'll answer those, and then we will eventually get to the ski problem, where we actually use this stuff instead of just throwing vocab words at you and equations.